Listen up, boys and girls, because today we are going to talk about complex numbers. Now, as we talk about complex numbers, what we're going to talk first is imaginary numbers and where they come from and how they relate to complex numbers. Then we're going to talk about plotting complex numbers. We can put them on a graph, which actually will help us do the third thing we're doing today, which is finding the absolute value of a complex number. And the last thing we're going to do is operations with complex numbers. Operations meaning adding, subtracting, multiplying, and dividing. So that's our lesson for today. Now, you may ask, what are imaginary numbers? If you've not used them before, it can seem weird to have a number that's imaginary, but let me explain to you what's going on here. You probably are already aware, although if you're not, it's okay, that you can't really find the square root of a negative number. I mean, a lot of times people try, and they'll tell me the square root of negative 4 should be 2. The problem is that 2 times 2 is positive 4, not negative 4. So then, of course, you think, well, then it should be negative 2. Except the problem with that is that negative 2 times negative 2 is also positive 4. You can't square a real number and get a negative result, because the negative times a negative makes a positive. So, sometimes people will say things like, well, 4 times negative 1 is negative 4, which is great, except that's not what square root means. For square root, we're looking at a number that you can multiply by itself to get negative 4. So this brings us to the conclusion that you can't find the square root of a negative number. And that is certainly true. Although this is actually a different statement from the statement that negative numbers have no square roots. Because just because you can't find one doesn't mean that it doesn't exist. So people have been arguing about this for a long time. Although one day a mathematician said to himself, and I don't know why he reached this point, he may have been very desperate to come up with some new math, or he might have been just really drunk. But he said to himself, well, what if these numbers did exist and we just don't know what they are? What would that look like? Which turned out to be a very interesting question. And when he started thinking about this, what we realized as mathematicians is we only need one of these to exist, and we can find all the others. So what we do is we set up one number that doesn't really exist, but we're pretending it exists, in the same way that we can talk about unicorns or have arguments about what zombies can and can't do, even though none of those things are real. We can talk about the square root of negative 1. We call it I, the imaginary unit, I, and it's the square root of negative 1. Now what that means is if you take this number, I, and you multiply it by itself, you get negative 1. It's important you understand this is not a real number. It's made up, so we call it imaginary. This, however, gives us the ability to start talking about all of our negative square roots of negative numbers. So for example, the square root of negative 4. Just like we did with our other square roots, we can split that up as the square root of 4 times the square root of negative 1. The square root of 4 is 2, and the square root of negative 1 is I. Why? Because we said it was. So 2I, if you square it, you'll get 4 times negative 1, because remember I squared is negative 1. So if you square this number, you'll get 4, and I squared is negative 1, so you'll get negative 4 if you square this number. As another example, the square root of negative 45, if we split that up, we pull out the negative as negative 1. 45 is 9 times 5. The square root of 9 is 3. The square root of negative 1 is I. And the square root of 5 is just the square root of 5. You can't simplify that bit. So we can start talking about these square roots with negatives inside by using this letter I, which is our imaginary unit. This sets up a whole new set of numbers. So we've been dealing with the real numbers exclusively so far. Now what we actually have are imaginary numbers, although so far we've only seen pure imaginary numbers. So for every real number like 1 or 8 or 1/4, the square root of 2, these are all real numbers. Each one of those has actually an imaginary counterpart when you multiply it by I. So 1 times I is I, and 8 times I is 8I, and 1/4 times I is 1/4 of I, and then square root of 2 times I is I square roots of 2. And those are all what we call pure imaginary numbers. They're purely imaginary. The problem is that real numbers and imaginary numbers do not get along well. They're not like terms. So when you try to add them together, you get a whole different set of numbers, which are the sums here. So we can take 1 and try to add it to I square roots of 2. but they're not like terms. They can't actually go together, so this is just what you get. And notice it's part real and it's part imaginary. Square root of 2 plus 8i, another example. We can do 8 square roots of 5 plus I square roots of 2. Making up these as I go along. 3 plus 4i. We'll see that one later. 6.5 minus 9.1i. These are all combinations where they're not purely imaginary, nor are they real. Now it turns out we call this whole, anything that's not a real number, we call an imaginary number. So the real numbers are the ones with no i's at all. And so then whether it's purely imaginary or a combination of imaginary and real portions, we call all of these imaginary. They're not real. The whole set is called the complex number system. That includes the real numbers and all of the imaginary numbers. We define this basically as any number that can be written in the form a plus bi, where a and b are real numbers. So you've got a real part plus a purely imaginary part. That's a complex number. Now that includes numbers like 8, because we just have to make b equal 0. Right? 8 is 8 plus 0i. So really all the real numbers are just the numbers where b is 0. And the purely imaginary numbers, like I square roots of 2, are the ones where a is 0. Although I should point out, if both a and b are 0, what you have is 0, which we consider to be a real number. Then of course you've got all these numbers over here, which have neither one of them be 0. They're not purely imaginary nor purely real, although we still call them imaginary. And that's the complex number system. So once you understand the whole a plus bi part, you're ready to start talking about the complex plane. That is how we graph these. Notice instead of an x and a y axis, what I have here is an r, that is a real axis, and an I, imaginary axis. And we're going to graph numbers like 2 plus 8i the same way we would graph an ordered pair, x and y pair. 2 is the real portion, so we find 2 on the real number line, and 8 is the imaginary portion, so we find 8 on the imaginary axis, and that gives us a point at 2, 8 there. That's 2 on the real axis and 8 on the imaginary axis, and that's 2 plus 8i. Similarly, if I have negative 4 plus 3i, I'm going to find negative 4 on the real axis and 3 on the imaginary axis, and that's negative 4 plus 3i. You can also graph numbers that are real. Notice 6 is 6 plus 0i, so it goes over here at the point 60. Ciao. Similarly, negative 4i is 0 minus 4i, so it goes down here at 0, negative 4. So we can plot real and imaginary and really all complex numbers on this complex plane. Once we figure out how to graph these on the complex plane, we can start finding their absolute values, which is number 3 on our list here. Absolute value of a complex number. If you remember when we talked about absolute value, back when we were dealing with just real numbers, what I said was that how far it is away from 0, which is still the case. The absolute value of 6 is 6 because it's 6 spaces away from 0. It's a nice straight line. You can count the spaces. It's 6 away. And so this is still a good definition, how far you are from 0. But the complex numbers that are not real nor purely imaginary are at diagonals away from 0. So in order to figure out, say, the absolute value of this negative 4 plus 3i, I have to find this straight line. And the easiest way to do that is to construct a right triangle, because we know the legs of our right triangle. It's negative 4 over and 3 up. Right? So negative 4 and 3 are the two legs. And since this is a right triangle, the third side C, which is the distance that this point is from 0, is going to satisfy the Pythagorean theorem. C squared equals a squared plus b squared. So C is going to be the square root of a squared plus b squared. Now, since I know what those are, I can just plug them in. Negative 4 squared and 3 squared, that's 16 and 9, which makes the square root of 25, which is 5. So the absolute value of negative 4 plus 3i is 5. Let's do 2 plus 8i as well. Note this triangle has sides 2 and 8, so the square root of 2 squared plus 8 squared is 4 plus 64, which makes the square root of 68. Oh, that one's irritating. 68 is a multiple of 4, that's 4 times 17, so we get 2 squared to 17. That's the absolute value of 2 plus 8i. Notice the absolute value is always a real number. And you just take the a part and square it and the b part and square it, add them together and take the square root. That's the formula. It's the Pythagorean theorem solved for c. A squared plus b squared, and then take the square root. That'll work for the ones on the axes, although why bother squaring them and taking the square root? You can just count however far they are away from 0. As far as adding, subtracting, and multiplying and dividing complex numbers, if you're going to add two complex numbers together, just remember the i's, the imaginary parts and the real parts, are not like terms. So for adding, you just combine like terms. The 2 and the 4 go together and make 6, and the negative 1 here, negative 1i, and the 9i makes 8i. Combine like terms. Similarly, for subtracting, we're going to add the opposites. You could subtract. I find I mess up when I start subtracting, because subtracting negatives and like a negative minus a negative, it just gets confusing to me. So I add the opposite. 2 minus I plus. Now notice I negated both the 4 and the 9i. You distribute the negative sign here, and you get 2 minus I plus negative 4 and negative 9i. That gives you negative 2 and negative 10i. So adding and subtracting is just combining like terms. It's important you check for the operation there, because the multiplication and the addition look kind of similar at a glance, but addition you're combining like terms, and multiplication you are going to have to FOIL. These are binomials, you'll have to FOIL them. So when we FOIL, we get 8 and 18i and negative 4i and negative 9i squared. But if you remember from way back at the beginning when we started talking about I, we realized since I is the square root of negative 1, I squared is going to be negative 1. So this term here, negative 9 times I squared, becomes negative 9 times negative 1, or plus 9. So now the 8 and the 9 are the like terms, they make 17, and the 18 and the negative 4 makes 14i. So note the term on the end, the I squared, becomes negative 1, and then that portion becomes real. So multiplying two imaginary numbers together, you shouldn't have any I squareds left when you're done. Those become negative 1. So this is also a complex number. The product of two complex numbers is a complex number, a plus bi. Let's do another one, multiplication, just to make sure we've got this. Notice when I FOIL, I get 21, and 3 times 2i is 6i, negative 7i, and negative 2i squared. Remember, I squared is negative 1, so this becomes positive 2, and then I combine like terms. 21 and 2 is 23, and 6i minus 7i is negative 1. Division is a bit trickier, although if you remember that I represents a square root, what you'll notice here is that the I on the bottom is a problem because we're not allowed to have square roots on the bottom. All you have to do for division, you don't even have to divide, all you have to do is rationalize the denominator. We're going to leave it as a fraction, but we got to get this I out from the bottom. To rationalize the denominator with square roots, we have to multiply by the conjugate, which in this case is 1 plus 5i. You have to do that on top and bottom. The top you have to FOIL, so that's 2 and 10i and 1i and 5i squared. And the bottom, remember the inners and outers will cancel, so it's just 1 squared and negative 25i squared. Now remember, 5i squared is going to be negative 5, and negative 25i squared will become positive 25 because I squared is negative 1. So 2 minus 5 is negative 3, 10i plus 1i is 11i, and 1 plus 25 is 26. And this is the answer. Notice there's no i's on the bottom. You could split this into two fractions, but you don't really have to. Let's do another one of those. 6 minus 4i over 2 plus 3i, multiplied by the conjugate. You get 12 minus 18i minus 8i plus 12i squared over 4 minus 9i squared. So minus 9i squared becomes plus 9. So that's going to be 4 plus 9 is 13 on the bottom. 12, this 12i squared becomes negative 12. 12 and negative 12 makes 0. Negative 18 and negative 8 makes negative 26. Notice 26 divided by 13 is negative 2. Negative 26, I should say, divided by 13 is negative 2. So this one divided very nicely to be negative 2i. Well, that brings us to the end. So we talked about imaginary numbers. We talked about how to write complex numbers. It's always a plus bi. We plotted them on the real and imaginary axes on the complex plane so that we could find the absolute value. Remember, the formula is the absolute value is the square root of a squared plus b squared. And then we talked about adding, subtracting,